2.0.0 High force cable pulling. Describe how to set up the feeding end, describe how to support conductors, describe how to pull cable in cable trays. High force cable pulling is not usually done daily, although a large project may require several consecutive days of high force pulls. It's actually a small part of any electrical raceway installation. Workers may take days, weeks, or even months to install the completed raceway system. Cable pulling operation typically takes less time. There are several items to consider during high force cable pulling. Raceway system drawings must be studied and the installed system examined to ensure that it's properly installed and will accommodate the conductors. The conductors and pulling rope must be matched to the pulling equipment. Determine the best place to set up for the pulling. The chosen pulling equipment must have the proper capacity for the job. Having enough workers is critical, and safety must be foremost in everyone's minds. When planning a cable pull, make sure enough cable is on hand for the run. Cable may be verified while still on the reel by using a cable length meter. Of course, the conduit run length should have already been checked as discussed previously. Do not proceed further until everyone is assured that enough cable is on hand for all bends, sweeps, and junction boxes and other needs. If the cable falls short, take measures to correct the situation before continuing. A feeding sheave for pulling equipment will provide a smooth guide for the cable. Also have sufficient lubricant on hand and use it both before and during the pull. A sheave is like a pulley. It's a wheel or assembly of consecutive free spinning wheels used in cable pulls to reduce friction around turns, often referred to as pulley. Select and install the proper cable grips on the cable ends. Gripping must be adequate to handle the imposed force. When pulling cables in a horizontal run, the controlling worker simply reduces the amount of tension held against the capstan to slow down and reduce the cable pull tension. When the operator releases all tension, all pulling force is relieved. During the pull, make sure that the pulling rope remains free and is not wrapped around any part of your body. When pulling vertical runs, the rope must be tied off after stopping the pull to keep the cable from falling back down the raceway. The entire operation should be supervised from start to finish. Communications equipment must be used on both ends of the pull. Typical cable pulling setup is shown in Figure 22, including cable reels, reel stands, a conduit system, and other accessories needed for the pull. So here are the cable, the reels on jack stands, and they're pulling down. Here's the cable sheave so that they're going straight into the conduit and they don't have to rub on the side of the conduit. So they're going around a couple of bends, a 4-bend saddle, and a couple of 90s. Here's the cable pulling apparatus. Measuring pulling force. Monitoring the speed, pulling force, and distance pulled no longer requires the puller operator or supervisor to stand over the puller controls. The Greenleaf Smart Pull system provides this information to anyone connected to the supporting app. The data can also be saved to documents the conditions under which the cable was pulled. So it goes right to your smartphone. 2.1.0. Come on, don't jump like that. Feeding end of the pull. Here's the highlight. It says choose rope that has at least 4 times the strength of the required pulling force. For example, if the estimated pulling force is 1,200 pounds, the rope should be rated at no less than 4,800 pounds. Check the rope carefully for wear or damage before the pull. Remember that a rope is only as strong as its weakest point. Here's another highlight. It says the feed setup should unreel the cable along its natural curvature, as shown in Figure 23. So come off of the reel this way, and the natural lay of the cable, don't try to bend it back on itself. Here, reels on the truck with jack stands, and they're pulling down. Apply the lubricant here. They should also have a sheave up overhead to make sure that the cables are coming in at a straight shot into the conduit and not rubbing on the side of the conduit. Your sheaves to get the cable up high enough. Here's highlights for pulling around bends. Use a conveyor sheave assembly with the appropriate radius, such as the one shown in Figure 25. So here's a bunch of sheaves on a cable assembly or a sheave assembly, and you can use it for large radiuses going around cable trays. You can lie it flat, and it's a horizontal pull. It'll go around corners. Here are different sizes of sheaves. Sheaves must be positioned to ensure the curvature is smooth and the cables are deflected evenly at each one. Never allow a polygon curvature as shown in Figure 26 by placing sheaves too far apart. Here's 26. Yeah, these are too far apart, and it's going to put a lot of stress and strain on that cable. Try to make it a nice smooth pull. Supporting vertical conductors. Conductors in vertical raceways must be supported in accordance with NEC section 300.19. In general, one conductor support must be provided at the top of the vertical raceway or as close to the top as practical. Intermediate supports along the vertical run must be provided with spacing between them limited to the values specified in table NEC table 300.19a. The spacing is based on conductor wire size and material, either copper or aluminum. So conductor support refers to physical support provided for cables or conductors traveling vertically. NEC allows several different methods for supporting conductors and raceways. The following methods are typical. Conductors may be supported by insulating wedges inserted into the ends of the conduit as shown in Figure 27. Where clamping of insulation does not adequately support the conductor inside, the conductor itself must also be clamped. So they've got these wedges. You order them from a supply house, and you tell them how many conductors and of what size, and they'll have them specially made, and you can order as many as you need. The code book's going to tell you, like, if it's a vertical run, let's say, for instance, every 60 feet you have to have a support. So every 60 feet, you put a box, and you have the conduit end in that box, and then there's another conduit above it that continues on, and you can put one of these cable support wedges in each end of the conduit at each box, however far it goes. Conductors may be supported by inserting boxes at required intervals in which insulating supports are installed and secured in a satisfactory manner to withstand the weight of the conductors attached to them. The boxes must have covers. Cables may be supported in junction boxes by deflecting the cable not less than 90 degrees and carrying them horizontally to a distance not less than twice the diameter of the cable. Cables are carried on 2 or more insulating supports and additionally secured to these supports by tie wires if desired. Where this method is used, cables must be supported at intervals no more than 20% of the values mentioned in NEC Table 300.19a. Cables may be supported by a method of equal effectiveness. And it says, caution when installing conductors in vertical raceways, install proper support before removing the pulling equipment or cutting the conductors at each end. A variety of supports are manufactured specifically for supporting cables in a vertical conduit run. Many ideas can be obtained from manufacturers' catalogs. Therefore, review the offerings from electrical suppliers and manufacturers' representatives whenever possible. Here's a highlight. It says, one concern is runaway, that is, cables falling down the raceway. This can injure workers on either end of the pool. Consequently, braking systems should be used on all long vertical cable pulls. Get specific instructions from your supervisor before beginning a vertical pull. And here's another highlight. Warning, guard against runaways in all vertical pulls. Make certain that proper braking equipment is used to stop a conductor fall should a runaway occur. (2.3.0) Pulling cable and cable trays. When long lengths of cable are to be installed in cable trays, challenges are frequently encountered. This is especially true when the cable must be pulled directly into the tray and when it changes direction several times. Cable pulling system must be planned and set up so that the cable can be pulled into the tray without damaging the sheathing and insulation. You must also avoid damaging the cable trays on their hangers. So here they're using sheaths in order to make the cables run around a smoother radius and not scrape the side of the cable tray. Also, they're using sheaths at intervals to support the cable, and it allows them to roll over the sheaths rather than drag across the rungs of the cable tray. Here's a highlight. It says, for heavier pulls, a pulling eye should be used. Care should be taken not to stretch the insulation jacket or armor beyond the end of the conductor, nor bend the ladder, trough, or channel out of shape. So in general, the pull exerted on the cables with a basket grip should not exceed 1,000 pounds. That's also a highlight. In general, the pull exerted on the cables with a basket grip should not exceed 1,000 pounds. Bend radius of the cable should never be less than the values recommended by the cable manufacturer. For example, the limitation for one specific rubber insulated 1-inch cable with no shield or armor is 4 times the diameter or 4-inch radius of the bend. NEC section 320.24 limits the bend radius to 5 times the diameter of interlocked armored cable. Cables with special construction features such as wire armor and high voltage cables require a large bend radius. Best results are obtained by pulling the cable in one continuous operation at a speed of 20 feet to 25 feet per minute. So it should be one continuous operation. Pulling the cable in one continuous operation. I'm going to highlight that portion of that sentence. The diameter and length of pulling line depends on the pull being made and the tools and equipment available. Winch and power units must be of adequate size for the job and capable of developing the pulling speed required for the best and most economical results. Here's another highlight. It says sheaths must be supported in the opposite direction of the pull. For example, right angle conveyor sheaths should be supported at 2 locations as shown in figure 28 to compensate for the pull of the cable. Okay. Warning at first sign of any problem that presents a danger to workers or cable, the pull should be stopped. Make certain that all communication equipment is properly in proper order before starting a pull. So make sure all communication devices are working. For very long pulls, some contractors use an auxiliary winch. Power winches may exceed their preset tension limits and abort the pull. So a second winch is installed in a high tension area of the pull in a straight section of tray. The second winch is used to pull a loop of slack cable and reduce the tension on the main winch. This leaves the main winch to pull only the length of slack cable between itself and the auxiliary winch. I'm not going to read that case history. Section 2 review. If the estimated pulling force is 800 pounds, the pulling rope should be rated for no less than, and then you remember how we multiply that. The requirements for intermediate conduit supports can be found in, and then you can look back in the text and see that. Armored cable should have a bend radius of no less than. All right. Let's go on to the next section. 3.0.0 Cable limitations when pulling. Calculate the allowable tension on a pulling device. Calculate the allowable tension on conductors. Calculate the sidewall loading. So here are a couple of highlights right off the bat. It says, while reels are in storage, either before or after a pull, the conductor ends must be sealed to prevent moisture from entering or creeping into the cable ends. So they need to be sealed. The minimum ambient working temperatures for cable pulling operations depends on the cable jackets. In cold weather, cable reels should be stored in a warm area overnight so that the cable jackets will be at the proper temperature for pulling the next day. They're more flexible. You don't want them to crack. Calculate and stay within the cable's maximum pulling tension, maximum sidewall load, and minimum bend radius. Ensure that the raceway joints are aligned and that the wiring space is sufficient. Avoid dragging the cable over the edge of the raceway. Use sheaths so it enters smoothly. If using a basket grip, secure it to the cable with steel strapping. Ensure that the elongation of pull rope minimizes jerking. Pull the capstan at no faster than 40 feet per minute. Do not stop a pull unless it's absolutely necessary, but safety is always the first priority. Never pull in the middle of a cable. Seal the ends with appropriate putty or silicone caulking and overwrap with tape until the conductors are terminated. Maximum pulling tension should not exceed the smallest of the following values: either the allowable tension on the pulling device, such as a basket grip, the allowable tension on the conductor, or the allowable sidewall loading. All right. Here are installation aids. Other tools available to simplify the pulling of cables include right-angle rollers, radius cable rollers, and framed cable rollers. Be sure to position them at the proper locations to prevent damage to the cable during the installation and to help the installation process as quick as possible at the minimum tension necessary. So here are some rollers that you can use. 3.1.0 Allowable tension on pulling devices. Do not exceed the manufacturer's working load of the pulling device. Pulling eyes, ropes, anchors, basket grips, or other equipment. If a catalog information is not available, work at 10% of the rated tensile strength. Tensile strength is the pulling force required to break a rope, wire, or structural beam. The allowable tension for a basket grip must not exceed the value of the conductors as shown in Table 2, or 1,000 pounds, whichever is smaller. Exceptions to this rule do occur, but rarely with the value exceeding 1,250 pounds. Note that you must know the area of the conductor being pulled to apply the values shown. Okay. So these are different tensions. 0.008 pounds per circular mil. Same with aluminum. The temper, either soft or hard or 3/4 hard. So it gives you different tensile strength for each circular mil. Allowable tension on conductors. The metallic portion of the cable is the strength member and should bear all the pulling force. Never use shielding drain wires or braids for pulling. Table 2 provides the allowable pulling tension for various types of conductors. Any wire or conductor will break if stretched beyond its tensile strength. Never exceed the calculated tension value. And reduce the maximum pulling tension by 20 to 40% if several conductors are being pulled simultaneously, because the tension is not always evenly distributed among the conductors. Maximum tension for a specific cable product can be found using manufacturer's data. In general, the maximum tension for a single conductor cable should not exceed 6,000 pounds. Maximum tension for 2 or more conductors should not exceed 10,000 pounds. Maximum stress for leaded cables must not exceed 1,500 pounds per square inch, or 10.3 megapascals of lead sheath area when pulling a wire with a basket grip. Maximum tension for non-loaded cables must not exceed 1,000 psi of insulation area when pulling with a basket grip. So for a straight horizontal raceway section, the pulling tension is equal to the length of the duct rod multiplied by the weight of the cable and the coefficient of friction. So the total pulling tension equals the length of the raceway run in feet times the weight of the cable in pounds per foot times the coefficient of friction. So for ducts having curved sections, the following equation applies. The tension at the bend equals the tension into the bend times the Amperian logarithmic base of 2.718 raised to the coefficient of friction and the angle of bend in radians. We don't need to do that calculation, so don't worry about it. Here's a chart. Table 3, coefficient of friction of various bends. So it gives you the degree of bend, and it gives you the value of the logarithmic times the coefficient of friction at the bend. So here's the coefficient of friction. If the coefficient of friction equals 0.75, then it's 1.22 for 15 degrees, 1.48 for 30 degrees, 1.8 for 45 degrees. If the coefficient of friction is 0.5, then your values are less, 1.14, 1.3, 1.48. And if the coefficient of friction is 0.35, they're even less still, 1.10, 1.20, 1.32. Okay. So check out that chart. 3.3.0, sidewall loading. For calculating cable pulling tension, sidewall loading or pressure must be considered. The sidewall load is the radial force exerted on a cable being pulled around a conduit bend or sheave. So here's a curved 90, and there's going to be sidewall loading. When you pull this around, there's a coefficient of friction, but there's also sidewall loading. So let's see what they give us a formula. In general, the sidewall loading on any raceway run should not exceed 500 pounds per foot of bend radius. This pressure, however, must be reduced on some types of cable. For example, Table 4 shows one manufacturer's recommendation for the maximum sidewall pressures permitted for various types of cable. Always refer to the cable manufacturer's guidance for the type of cable being used. So here's Table 4, maximum sidewall pressure for various types of cable. They're saying 25 kV and 35 kV, that's 1,000 volts, 25,000 volt cable, 35,000 volt cable. It's no more than 300 pounds per foot of sidewall pressure of the bend radius. So however many feet of bend radius is 300 pounds times those feet of radius. For example, figure 30 shows a simple raceway system containing three 500 kc mil lead sheath copper conductors. Note that the straight 300 feet run from A to B, a 45-degree bend, and then the other 100 feet straight run from C to D. So we have to figure those separately. We would figure the 300 feet times the weight times the coefficient of friction. We do it 100 feet times the weight of the cable times the coefficient of friction, and then we would do the 45-degree for that same cable. It says to find the calculated pulling tension from A to D, refer to the cable data from the product manufacturer. Suppose this cable weighs 8 pounds per foot and has a 0.141 inch thickness of sheath. The outside diameter of the 3-conductor cable assembly is 3 inches. Refer again to figure 30 and use 0.5 as the coefficient of friction and calculate the pulling tension from A to D as follows. Find the tension between points A and B. So tension at B is length 1 times the weight, so it's 300 feet times 8 pounds per foot times a coefficient of friction of 0.5. So it's 1,200 pounds. That's between A and B. Find the tension between points B and C. This is going around the 45-degree bend. Because the distance between B and C involves an angle, refer to Table 3 of this module. Looking in the left column of the table, we see that 45 degrees equals 0.7854 radians. This value multiplied by the coefficient of friction of 0.5 equals 0.3927. Next, find the value of E to the power of FA by locating the 45-degree angle of bend in the left column. Read across the row to the column with the 0.5 coefficient of friction. The number is 1.48. So A equals 0.7854 radians. FA is 0.5 times that is 0.3927, and the logarithmic value is 1.48. So we'll take the 1,200 feet times 1.48 equals 1,776 pounds. Therefore, the tension at point C is 1,776 pounds. And then the third step, find the tension between points C and D. That's 100 feet times 8 pounds per foot times the coefficient of friction of 0.5, so it's an additional 400 pounds. So we'll add that to our bottom line, and we get 2,176 pounds. basket grip used on this size of cable should not exceed a tension of 1,900 pounds. The 2,176 result in step 4 exceeds this amount. Therefore, if the pull is made from point A to point D, a pulling eye will have to be used instead. However, if this pull is reversed from point D to point A, the total pulling tension will be reduced. This is because the distance from point D to the 45-degree angle is just 1/3 the distance from point A to the 45-degree angle. So it reduces that tension, the coefficient of friction. Here they redid their calculation and they ended up with 1,792 pounds. So that's below the 1,900 pounds that they're able to use the basket grip. So in the final analysis, we see that pulling the cable from point D to point A reduces the pulling tension required. As a result, the pull can be reversed with no need for extra tools, or either a pulling eye or a basket grip must be used. It's important to note that the tension is reduced by feeding the cable from the end nearest the first bend encountered. Here's cable tray. They did a really nice job the way they laid these cables in and secured them, kept them all nice and neat. 3.0.0 section review. If catalog information is unavailable for a pulling device, do not exceed, and then you can look back on the reading. If several conductors are being pulled simultaneously, you should reduce the maximum pulling tension by, and then there was, again, go to the reading material and you'll find that. The maximum sidewall pressure for 5 kV power cable, you can look that up in that table and find it. This concludes 26206 conductor installation. And as always, I hope you got something out of it. If you did, give me a thumbs up and consider subscribing to my channel. It really does help. And as always, I'll see you on the next one.